Hi, welcome everybody to the January MAS meeting, if you didn't already know where you were. I believe that Mark wants to say a few words before we get completely into this.
I have less to say now. I have less to say now because we have less time.
Sorry.
No, it's not your fault. Well, thank you, Trena. Thank you, Trena, for volunteering to be the president. And I just wanted to take a few minutes just to basically thank everybody that worked with me and supported me. Mainly the board, you know, Volts, John, Trena, Matt, Conrad, Gunner. I think that's everybody. I think it covers the whole board that when I was on the board. And I mean, without them, I mean, it wasn't me, it was them. And, you know, the site leaders, it's not one person is running this organization. And I want to keep reiterating that it's the organization runs the organization. You've appointed the board to run the organization for the day-to-day operations. And trust me, the day-to-day operations it sounds simple, but in the background, it sometimes can be a little complicated. And, you know, with that, I'm happy that, you know, the 2 years that I served as president, it went quite smoothly for the most part. And it was very enjoyable and it's hard for me to call it fun. But for the most part, it was fun. I mean, there were those times, but I think that's just working with people and working with other organizations besides just ourselves. So I'm not going anywhere. I have some personal business I need to take care of. And I'll take care of that. But I'll be around. I have many things that I'm involved in that I'm going to continue to do. There's projects within MAS and there's some projects outside of MAS that I'm involved with, and I'll be around. So thank you, everyone. Thank you for your support. I appreciate it. And good luck, Trena.
Thanks, Mark. Yay.
The comment section of the program. Can I pick on you for a minute? Yeah. Okay, I know that there are lots of volunteer organizations out there. And this one in particular is kind of a hobby organization, right? It's something that we love to do. It's not, you know, building Habitat for Humanity. It's not, you know, raising money for feeding starving children. It's a hobby group. But Mark, in the last 2 years, you brought this up to such a great game. I've worked with other organizations and they don't have the level of organization. The stuff with the Constitution is absolutely critical. One day someone comes on, knocks on your door, and suddenly it's a lawsuit. To be able to go through the Constitution and make sure that we're protected from things like that, to have the organization, Matt, that you've provided in the Treasury, and to have the transparency of where we are every single month, and the documentation online that was just kind of somewhere in someone's garage that's stuck in a banker's box that was under a shelf. We've brought all that stuff out. We've put it where it needs to be. And you guys have really not just you, right? You had your team, the rest of the board members, but in the last 2 years, I've seen a real great change. And I think a lot of that's attributed to your leadership. So thank you very much for what you've done for the club.
Thanks, Ron. I didn't think we were going to talk about the Constitution anymore.
And this is why we're a club, because we have so much fun together. Well, thanks, Mark. I do appreciate your service there. You have a solar system. Think you're going to fade away? I doubt that. Let's see. I have a whole spiel, but I think Mark kind of took it all over. So we'll just go to the next slide. Because I'm your new president. I'm Trena, and hopefully I will be able to serve in the same or possibly better capacity than Mark did. We'll see. We'll check back in 2 years. And I would like to introduce the next board, the 2023, well, half the 2023 to 26 board. You've got, I know, isn't it kind of cool? I'm proud of that one. I'm proud of that one. We also have John in the building. He's our vice president, and Dave is here as well. And I've expanded on your mug, Matt, along with Conrad and Ahmed. And thank you very much for all of you that have volunteered to be on the board with me and haven't run away yet, but there's still time. We would also like to welcome some new members. We have 15 new members as of January 3rd. Thank you. And so I don't know if you're online, great. If you're in person, I'm not sure if I see any of them, but thank you very much and welcome to our astronomy obsession. So hopefully you won't get too deeply involved in it, but we hope that you do. And thank you for our volunteers that, like the board, Mark, everybody else, whether it's on our committees, working at a public star party, or even working behind the scenes, like website development, membership, outreach, and so many more. Each one of you makes this club run so well, and it's so very much appreciated. And it's all due to each and every single one of you. So thank you very much for volunteering. It really is great. So if anybody is curious, whether you're online or here in person and want to, come and see what it's about and what you can do, just check with one of the committees or even anybody on the board. We'd appreciate having a conversation with you. Next meeting, time goes by so fast. But our next meeting coming up is on, I put February 5th, but it's actually February 2nd. I was thinking this month instead of next month. So tune in, just a heads up. It is also going to be a business meeting because we're going to be reviewing the budget. So please attend. You'll need to register and do all that fun stuff to make this quorum and official. Yes, Mark. I know. I am. Listen. He's not going anywhere. See, if you come in person, you get all this wonderful camaraderie that comes around here. I know Mark has talked about Slack before, and I'm not going to tout too much about it, but I do know that I love using it. I know we love using it as the board. It just gives a great little texting plus to everything where we can have a group of people, instant communication, whether they read it or not, but it's there, it gives you notifications and it's nice and quick. And you don't have to worry about doing group texting because I don't love setting up group texting. It's a pain. I'd rather go on Slack and have somebody do that. So if you need to see what it's all about, come talk to one of us. I can show you the whole thing. And it doesn't have to be completely on mobile. You can do it on your desktop and behind secure firewalls. So just know that it's out there. And it's definitely will be used. The MAS has a YouTube channel. I know Mark has said this before, but if you're interested in astrophotography, Doug Neverman has, I believe, 4 videos up there. We have new member orientation on the channel. Steve and Rebecca have posted that, and it's a great video to watch. So if you need a refresher about what's about the club and its benefits, please go out there and check. We have the BSIG. We have 2 years of presentations for the BSIGs. So if you are, hold on, I'll get to you, Suresh. So if you missed anything about the monthly meetings, you can certainly have a chance to go back and rewatch them. I did that when I was trying to do this presentation and what to say to all of you people, because I kind of sort of tune out Mark sometimes. So it was good for me to rewatch that. And the Loaner Scope program. It is a great program. I'm going to have Antone come on when he can unmute and just interrupt me. I love it. That's how I started out on when I joined. I borrowed a 5-inch SCT, I believe, and had a great time. And now, all right, go ahead, Antone.
Sure. Our Loaner Scope program is still in progress. About Even now in the depths of winter and our snowstorm, about half of our telescopes are out on loan. Members, as always, can request a telescope on the website under membership loaner program. And there's a form to fill out. We have Dobsonians, both 8 and 10 inch. We have some Cassegrains, some refractors, parabinoculars, and a solar scope. And yes, so in last year, we made 94 loans in total. The previous 2 years were 87 loans each. And for those of you who like to look at data and numbers, and given who I'm talking to, there's probably more than a few of you, you can see on the simpler chart on the left by type. So our 8-inch Dobbs went out 22 times, and our 8-inch Cassegrains also 22 times. So you can get an idea of the popularity of different kinds of telescopes. We also have our DVD, our great courses, and you can request those on the website as well.
I love them. I have one right now that I'm halfway done with. I've actually checked out a couple of those. So thank you, Antone, for doing that. I appreciate it.
You're welcome.
Yep. COVID, as always, we're still in that phase. But basically, if you're sick, stay home. That's where I would be. When I had it, it was great. I would get trapped in my bedroom. Before the next meeting, we get to have the Earth at perihelion. And I believe, what did I say? That was January 4th. And then we also have so many planets that are close to the moon, let alone themselves. You got Venus, Saturn, Jupiter, and it's great to have them. So if you have some pictures, maybe we'll post a couple of those next month. But this is also a good one for the 2 of you, because that is one of those extra little requirements that you can throw in there to sketch the moon and a planet. And I think you can have 5 or 6 of them. So that would help. If you're close to getting it done, here you go. Here's your month. Did you see it? Talking about the occultation. So yay! I did. I went out. I sat in my car, looked through the sunroof with binoculars. It was great. But if you're interested in seeing some other close-up ones, we have a Slack channel. We have astrophotography on Slack. And there's a lot of people that post pictures up there or videos that they've taken of it. It's something that the forum doesn't give you the access to do very easily. So I would certainly check it out. I mean, it's just, I loved watching them. So they're really, really pretty cool. Oh, okay. Okay. Dean was saying there's some good pictures on the forums too. So I haven't been out there much. Star parties. I know we all want to get back outside. However, it's cold. So I just wanted to that it's not too far away. Eagle Lake is going to have opening in March, hopefully, weather provided. CGO, you could still go out, just bring a snow shovel. I don't know, or park on the gravel. We do pile a parking lot at CGO, but I would still recommend, if you wanted to get into the observatory, bring snow shovels, boots, hand warmers. LLCC will do theirs or resume theirs in April, and just take a look on the forums for that one, because I know it's posted as every spring for which weekends that we can go up to. Beginner Special Interest Group. I know last month Claire did the winter hexagon, and that was wonderful. So thank you, Claire. Yes. You had 37 people watching. So that was pretty awesome. Yes, exactly. Yep. Suresh, did you want to talk about your needs for it? Well, don't you?
Okay.
Well,
So,
because I don't have that updated.
no, this is January 7th, though. Who's? I'm sorry, my bad. He doesn't February.
Yeah, Steve.
Okay, Suresh is confused and he's trying to confuse the rest of us. This is Steve. I've got the one that's coming up this Saturday, and it is a relatively simple one. It is designed for beginners. It's basically aids to navigating the night sky, talking about, I'm an old fashioned Luddite, so I use a lot of paper-based ones, but paper-based ones plus apps on your mobile phones and PC-based apps and stuff like that. So a little smattering of all of that stuff. And then the next one after that sounds like it's going to be Dave. So here he goes.
Okay, so in February, some of you may or may not know that I recently traveled down to Chile and was able to visit in somewhat detail the 3 of the research observatories down there, Cerro Patron, Cerro Tololo, and Alma. The first 2 have a total of like almost 50 telescopes. And Alma, of course, is a radio telescope site that has 66 radio telescopes that are joined together through interferometry. And I'm going to talk about my trip and some of those telescopes. So February 11th, yes.
Thank you, Steve, and thank you, Dave, for taking care of our beginners. Gemini articles. Everybody knows of them and wants to read them. So please get your articles set and ready and processed and sent to Father Brown by January 10th. I know it's not very long, but he's always looking for them. And I'm hoping at some point Mark will write an article about being president for 2 years. Or any of his adventures in astrophotography or anything else. He's shaking his head no, but I know he will. Hopefully. Emails, hopefully you got the last one. And just as a quick reminder, send it out to secretary on the Thursday before you want it published, and we'll send that up and get it out on Tuesdays. There's my thing. Okay. Astronomy League Awards. They are what I work on, which Claire works on, and a lot of people work on to get PINS certificates. It's a great way to learn the night sky. I can't tout that enough. I will boast about it. And I'm trying to become like Jerry with a bunch of pins. And I finally did get my sunspotter one, which is really kind of cool. I love it, except it really does get heavy, but it's okay. But we do have 2 to celebrate this month, and they are both to Dave Tostson. He completed his asterisms and the multiple star systems. Yay! Huh? A lot. He's completed a lot. I mean, I'm sure he has. Yeah, I'm sure if he was available, he would tell you. He probably knows all of what he has. If not, we'll ask Jerry next time. We'll find out. But hopefully, I hope to see somebody new up there, maybe, or in addition to Dave next month, and get there so we can, talk about it and what's good, what's bad, what is thrilling about it. I'm always interested. It's always good. Better know a constellation. We don't have one at this particular meeting, and next meeting is going to be the budget meeting along with our presenter. So I'm looking for a volunteer for March. If I can, draw a name out of a hat, that would be kind of great, but we gotta have a volunteer. So whether you're at home or here in the meeting room, it's very easy. Claire puts us all to shame on how well organized it is, but it doesn't have to be fancy. It could be just simple slideshows. I made one like for our meeting presentation here. I'm not doing it though. It only took a couple of weeks. You'll have plenty of time. So let me know, send an email to president or secretary that you're going to volunteer. Much appreciated. As I said, next month is February 2nd, not the 5th. And that is a business meeting. So you will need to log in and register for Zoom, and you'll have a sign up sheet here in online or in person, sorry. So because we do need a quorum to pass the budget, which I know everybody is very interested in. So Love numbers. Just love them. Don't we? Don't we? Yes, of course. Of course. It's what makes our club run is the numbers. You want fancy things? You got to give us numbers. It's lovely. And then we have our next month's speaker, which is Michael Rudowski. Hopefully I said that right. I'm sorry if I messed it up. But we do appreciate our speakers. Ahmed does a great job of getting our speakers. So, and tonight's presentation will be from Dr. Vuk Mandic. Yes. And he is with the Minnesota Institute of Astrophysics and Astronomy in the Twin Cities location. He has done work with LIGO, CDMS, and LISA, focusing on the area of experimental cosmology and astrophysics. And tonight he's going to be talking to you about gravitational wave. So wonderful. Welcome, Doctor.
Okay. Can you hear me all okay on Zoom as well? Okay. Well, first of all, thank you very much for the invitation. It's a pleasure to be back here, actually. I was here about 6 or 7 years ago, I think, when the first detection of gravitational waves took place. Over that period of time, 6 or 7 years, a lot has happened. So what I'll try to do today is maybe bring it closer to home, that this is actually a new way of doing astronomy and astrophysics and cosmology as well. And it's picking up steam. There is a lot that that has happened and that we expect will happen over the next 5 to 10 years. So I'll try to give you a sense of where this field is going and what we have accomplished and what we hope to do. And I hope that you guys don't remember very well what I said a few years ago, because some of these slides are probably a repeat. Anyway, I'll talk about gravitational waves. Gravitational waves are a prediction of general relativity. So this is not something that you get from Newtonian physics. And general relativity, of course, is one of the most sophisticated theories we have. It is mathematically fairly advanced and so on. Takes a lot of effort to actually do calculations with it and so on. However, the intuition that goes with it is actually pretty straightforward to grasp. And so what I'll try to do today is I'll stick to the intuition, because I think we can get very far with it without going to the equations. So I'll focus on this picture on the right here rather than on the left. General relativity, of course, comes with Einstein. So back in 1915, so a little over 100 years ago, he wrote down his famous Einstein's equation. And the equation basically puts on one side of the equation is mass or energy. On the other side is space and time coordinates. And he basically gave us this, in my mind, really incredible insight that if you have a region of space that has some mass or energy in it, the space will be curved. And he wrote down this equation, specifies explicitly how this curvature takes place, exactly what is being curved in which way and so on. There's, again, a very good intuition. So this schematic here shows, gives you basically an intuition of how this happens. So imagine you have just a sheet of linen, for example. You stretch it out, it's flat. That represents our flat space. And then suppose you take an apple and you throw it into the middle of it, right? The sheet will get distorted. There'll be some curvature, if you like, around where this mass is. And then you take a marble and you toss it across the sheet. So here it is, a marble comes in here on this side. It's traveling more or less in a straight line, but as it encounters this curvature, this deformation in the linen, it turns and comes out in a direction that's different from the initial one. And this is basically how we think of gravity in general relativity. There is no gravitational force in general relativity, but what there is just curved space. So if you have a mass, it will it will curve the space around it, and the shortest distances will no longer be straight lines in this curved space. They will be, turns out, conic sections, parabolas, hyperbolas, ellipses, and so on. Which explains why, for example, we have elliptical or circular orbits or hyperbolic trajectories and so on. Mathematically, it just works out beautifully. So that's the basic idea. This picture here is just another way of visualizing. We have a sun and the earth here, and both of them are curving the space around them, one more than the other, of course. And then this shortest distances in this curved space are basically like the circular trajectory of the earth around the sun and so on. Okay, so what Einstein did was he took his equation and he looked at it in the limit when the gravitational field is very weak, so far from the masses or far from any energy. And he found that this equation, which is a very complicated equation, it's actually 10 differential equations bundled in one. This equation boils down to a very simple wave equation. It's an equation that describes, for example, sound waves traveling through air, or water waves, or light waves. It's the same equation mathematically, but what waves in this case is the space itself. The way we call it the metric. It's the way we measure distances between objects in space. That's what changes over time. That's what waves. What the physical manifestation of these waves turns out is basically shown with these two rings. As the gravitational wave propagates through space, it will shrink and stretch dimensions that are orthogonal to the wave propagation. So if we have a wave that's propagating, say, perpendicular to the screen, it will stretch and shrink the two orthogonal dimensions in an alternating manner. So if we have a ring of test masses, like shown here, and they're just freely floating in space, they're not reacting or interacting with each other in any way, this perfect circle of test masses will get deformed into an ellipse, maybe first elongated around the vertical direction, then a little later elongated around the horizontal direction, and so on. And this oscillation will take place as the wave propagates through the screen. Okay. And the two images here correspond to the two polarizations. Turns out there are two polarizations of gravitational waves, just like there are two polarizations of light. And in the case of gravitational waves, the two polarizations are just 45-degree rotations of each other. So is that okay? You guys okay with this? I mean, it is a leap of faith to some extent to accept this. Yeah. So you choose your coordinate system first. So imagine that I chose this coordinate system that's basically the plane of the screen. In that plane, all gravitational waves can be written as a combination of these two modes. If I chose a different coordinate system, rotated, let's say, with respect to the screen, I would have maybe two different modes. But again, every gravitational wave could be written as a superposition of these two. Yeah.
There it is. Okay. I guess I'm surprised it's at 45 degrees and not 90 degrees. Why is that?
Yeah, that's a good question. So it's there is a very nice physical way of explaining this. It has to do with the fact that electromagnetic interaction is transferred with photons, which are vectors, whereas the gravitational waves, or the equivalent of a photon in gravity, would be a graviton. That's a tensor. It's a spin 2 particle, if you're familiar with that. And spinors rotate differently than vectors. Whereas rotation if you wanted to make a full rotation of a vector, it's dealt with 360 degrees. for a tensor, you go only 180. Right, so you basically transform the tensor by twice the angle. Yes, yes. Yeah, they are independent. Great question. All right, so was there another question? Yeah. All right, so this is this equation here is Einstein's equation, probably in the simplest form you can write down. The thing on the left, this G mu nu, is the Einstein's tensor. So mu and nu are indices that run over the time and 3 spatial directions. So both mu and nu can take 4 different values. G itself includes 2 derivatives inside. It's a way of capturing curvature in space. So this tensor is basically designed to capture this curvature. And then T on the other side, T mu nu, is the stress energy tensor. This is where things like mass and energy show up. And of course, what Einstein did was he put an equal sign between them and he put a constant. He had to put a K in there in order to make the units work out, right? The thing on the left, this G, has units of 1/meter squared. The thing on the right has units of Newton per meter squared. So K by itself has to have units of inverse newtons in order to make the equation work. And in general relativity, there's only one way. You can come up, start with some fundamental constants and come up with something that has units of inverse newtons. Namely, you take the Newton's constant G, which is a very small number, and you have to divide it by the 4th power of the speed of light, which of course is a big number. So K turns out to be exceedingly small. It's about 10 to the minus 44 in the standard system of units in inverse newtons, which means that, yeah, I can wave my hand and I'm creating gravitational waves that are propagating through this space, but I'm shrinking and stretching the space in this room by 1 part in 10 to the 44, roughly, right? So it's incredibly small, right? I mean, it's hopeless. This has 2 consequences. One, if I want to have a measurable curvature, something that I can actually measure realistically, I need to have huge T, right? Because K is so small, T has to be very big in order to counteract the smallness of K to give me something reasonable for G, right? And that means basically that, you know, me waving my hand is just not enough. I need to find something much more massive moving at much higher speeds, smashing them together, things like that. So catastrophic kind of astrophysical events. The other thing that's the other consequence of this is that once you create the gravitational waves, right? Once you have some cataclysmic event that generates them, they keep going, right? It's very difficult to change them because again, you need some huge T, huge energy to change it. And that has a very unique implication. If you have gravitational waves that are generated at the Big Bang, they would propagate until today basically unperturbed. So if you could see them today, you could actually have some way of probing or testing or learning about the universe as it was being created. And that's a very unique prospect of gravitational waves, because nothing else, photons, neutrinos, or anything else you can come up with, nothing else goes, carries information from the universe when it was less than about a minute old. At about 1 minute after the Big Bang is when we expect the nucleosynthesis happen. This is where hydrogen, helium, and the lightest nuclei were formed. And then after that, you know, that part is nuclear physics. We can compare those predictions with, you know, how much hydrogen we see in the universe and so on. These things match up very well. So we think we know all that stuff after 1 minute, but there's basically no observational evidence for that first minute. And it's also, that first minute is also associated with very high energies, much of which is actually not reproducible in laboratories. So we don't really have a way of probing it, which is why this is actually the reason I entered the field. All right, so we need cataclysmic events. And here is a good candidate. We actually know this is the best one. This is the merger of compact binaries. Okay, so what does that mean? First of all, by compact, I refer to massive objects on the scale of a star, but compactified to very, very small dimensions. And this can happen in, well, multiple ways, but this picture here shows a typical life cycle of a star. The top branch that you see would be a star like our sun. So a star that's similar in size to our sun. As it burns its hydrogen fuel, eventually it will run out. It will go through this phase of the red giant, and eventually it will become a white dwarf, which is an object that's the size of about the Earth. So much smaller than the sun, much more dense than the sun is today, but still on a pretty large scale, right? The radius of the Earth is about 6,000 kilometers. The bottom branch here applies to more massive stars. So if you have a star that's maybe, let's say, 2 times more massive than the sun, it will go through the supernova after it runs out of the nuclear fuel. The gravity will be strong enough that it will overcome whatever pressure, thermal pressures exist in that star, and the star will collapse. Basically, the collapse will be stopped by the nuclear forces between the protons and neutrons and so on that exist in the star. So at that point, what you have is basically all of the nuclear material. So all of the protons and neutrons in the star, they get squished together into a giant nucleus, if you want to call it that, which we refer to as a neutron star. And that's basically all of the mass of the star now squished into an area of about 10-kilometer radius, right? So the size of the St. Paul or something. Much more compact, much more dense. In fact, that is probably the densest form of matter we know. Now, if the star is actually even more massive, so something like, let's say, 10 times more massive than the sun, then in that case, gravity will be stronger than even those nuclear forces between protons and neutrons. And so those nuclear forces will not be able to stop the collapse, and the star will collapse to a point. That's what we refer to as a black hole. So black hole is an object that has no size, theoretically speaking at least, but has the mass of the original star that gave rise to it. Okay, so there we have 2 candidates, neutron stars and black holes, which are very massive. So on the scale of a sun or several times the sun, or maybe 100 times the sun. If you have 2 of those, 2 such objects that are gravitationally bound, they will rotate around each other. And as they do so, as they rotate around each other, they will create gravitational waves. They will emit them. The gravitational waves will take away some energy. The 2 stars will get closer together, and over time, they will get closer and closer together and eventually merge. So this picture actually gives us an idea of what the gravitational wave signal would look like in such a system. When the 2 stars, 2 objects, let's say 2 neutron stars or 2 black holes, when they're far apart, they rotate around each other slowly. And we have this first part of the signal, which is relatively slow oscillation, and also small amplitude because they're so far apart. They're not modifying, they're not changing the space dramatically. But as they get closer and closer together, they speed up, right? And as they do that, they produce gravitational waves at a higher and higher frequency. The oscillation becomes faster, and it also increases in amplitude because they're closer together. They're more warping the space more. So the signal starts off slow with a small amplitude, increases in both frequency and amplitude over time, and eventually there's a merger. And after the merger, there could be some ring down during which or through which the new remnant, presumably a new black hole, settles down. This particular waveform, this particular system can be studied in a quantitative way. A lot of this can be actually computed analytically. And of course, the latest phase, the merger and the ring down, they are more, they require more sophisticated numerical techniques to actually solve the problem. But those have been done now for a couple of decades, or maybe not a couple of decades, but something like 10, 15 years. Those predictions now exist. Yes. So the question was, what is happening when the black hole is ringing down? And basically the picture you could have, in fact, we'll have a simulation in a minute. So maybe we'll go through that, and that'll probably clarify it. All right. So that's one candidate for gravitational waves. In fact, this is the type of gravitational waves we have seen so far, coming from mergers of two black hole or neutron stars. This is not the only type of gravitational wave source that could be out there. There are many others. There are many transient events, as you know better than me, in the universe. Things like supernova explosions, which are asymmetric. They could produce gravitational waves during the explosion. There are periodic signals like pulsars, which are neutron stars that spin at frequencies that could be in the hundreds of hertz or even kilohertz. And those spinning neutron stars, if they have some non-uniform mass, think of it as having a mountain on the surface. As it spins, it will produce gravitational waves that are actually twice the frequency of the rotation. And then there is the Big Bang itself, which I mentioned already. There are multiple processes that we think took place in the early universe, things like very rapid expansion, the inflation, and then also probably multiple phase transitions as the universe cooled during the first few seconds. Those processes could have produced gravitational waves in a very messy way. This would be what we refer to as a stochastic background. The signal would not have a particularly well-defined waveform. It would be a random noise, just a background hum that's left over from these early universe processes. And those stochastic gravitational waves could basically propagate until today. And if we could observe them, as I mentioned earlier, we could actually study the processes that took place in the early universe. All right, so this is you know, how much I wanted to say about the sources. Now, how do we actually detect these things? So there are multiple ways to do that as well. The one that I'll focus on today is based on interferometers. And the basic idea of an interferometer is you take a laser beam and you send it in here from the left. You pass it first through a mirror that's called a beam splitter. And the beam splitter basically allows half of the light to go through, the other half is being reflected. And so now we have two beams, one along the horizontal, the other along the vertical arm shown here. And then we put in two mirrors. The end, we call them end test mass Y and end test mass X. These two mirrors reflect the two beams back, and then they superpose back at the beam splitter, and we observe the output at the detector. So why does this work? Why for detecting gravitational waves? Remember that the physical manifestation of a gravitational wave is that it will stretch or shrink space. But in a very particular way, it will shrink one dimension while stretching the other. So if you imagine a gravitational wave that passes through perpendicular to the screen, before it arrives, the two arms, let's say, have exactly equal lengths. So when the two beams come back to the beam splitter, they will be in phase. They will perfectly superpose, and that could, for example, if you tune things correctly, it will mean that no light is coming out towards the detector. But if the gravitational wave passes through, one arm will be slightly longer than the other, and the two beams will be superposing in different ways as the gravitational wave passes through. And that will result in an oscillation of light at the detector. Okay, so have a very nice animation of this made by my colleagues at Caltech. So I will play the animation, and then let's see how it goes. So we have a laser. I'll stop it for a second. Here's the laser. Here's the beam splitter. You see the laser coming in this way. half of it goes through, half of it is reflected. The two beams come back and we observe them here at the detector. Okay, so now we will zoom in a little bit and you'll see now the laser beam, which is a wave itself coming through. You see that it gets split through the beam splitter. We're following one arm now. It bounces off of the mirror, it's coming back. And now you see the other one coming back from the left as well. And now they're superposing. And at the moment, the two waves are exactly out of phase. The peaks of one line up with the troughs of the other. They cancel each other out and no light is observed here. But as the arm lengths oscillate, stretch and shrink, you see that these two waves come in and out of phase. And that changes the amount of light at the detector. So that's really what we do, right? That's what these detectors are designed for. You measure the amount of light coming out of the interferometer, and that tells you about the relative lengths of the two arms of the interferometer, the X and Y. And if they're exactly equal to each other and not changing over time, then there's no gravitational wave that you're seeing. If one is stretching, the other was shrinking, that will give you some fluctuations of light at the detector that tells you a gravitational wave is passing through. And you can measure the waveform of it and so on, and study its properties, etc. Yeah. We have a question here.
Question. With an apparatus like LIGO, is there a minimum distance you have to have the arms in order to pick up the phase difference?
Yes, there is a limitation. There always is limitation. It has to do with the noise in the detector. So no matter how well you build your detector, there will always be some electronics noise or limitations based on the number of photons we have in the interferometer and so on. And this is continuously improving. So at the moment, we're at the level of about measuring about 10 to the minus 19 meters. I'll show you a little bit more about that a little bit later. But that's the level of sensitivity that these instruments have these days.
And we have a question on the chat. Does shorter wavelength light make this more sensitive? And so I'm just curious also what color you're using right now.
Yes, that's a very good question. The shorter the wavelength, the more sensitive the instrument would be. We're using laser at 1 micron wavelength. This is basically driven by technological reasons. You need to have a very stable laser, high-powered laser. And it turns out that neodymium YAG lasers are just the best thing at the moment. Now they're going forward, people are looking into other possibilities as well, and that may change in the future.
And I guess my own curiosity is you talk about 10 to the minus 19th meters. And that would seem to not even be an entire quarter wavelength or anything of the light. So you're looking at very small phase shifts.
That's right. So you may ask, how can you measure 10 to the minus 19 meters with the wavelength that's 10 to the minus 6 meters? Right?
Exactly.
Excellent question. So the way the reason this works is because our laser beam has many photons in it. So you can think of each length measurement is being done not by one photon, but by about 10 to the power 20 of them. And when you repeat the measurement, when you do a measurement n times, you improve your sensitivity by the square root of n. So that gives you, just right there, it gives you a factor of 10 to the 10. So that brings you to the 10 to the minus 16-ish. And then we also have an additional, we play tricks with this. We don't have a simple interferometer that I've shown you. We actually put additional mirrors in there to recycle the light and make it bounce back and forth many times before it gets lost. And that effectively increases our arm lengths by of order 100. And that effectively improves the sensitivity, reaches that 10 to the minus 19-ish level. Excellent questions. Okay, this is our network of gravitational wave detectors, more or less as it was 6 or 7 years ago. you see there are two LIGO detectors at Hanford and Livingston, Hanford in Washington State, Livingston in Louisiana. GEO 600 is a shorter arm detector in Germany. It's not as sensitive, but it is used for prototyping. And at that time, as of 2015 or so, Virgo and Kagra were not yet operational. Virgo is now operating in Italy near Pisa, and Kagra is in the Kamioka mine in Japan. Also started working a couple of years ago. And then LIGO India is the third LIGO detector that we hope will come online in a couple of years. It is now currently being constructed there. So LIGO stands for the Laser Interferometer Gravitational Wave Observatory. So it is exactly an interferometer type detector that I described earlier. You have the pictures of the two sites. Hanford is basically in the eastern Washington state. It's in the desert. It's I think just about an ideal place to put a detector of this kind. Livingston is in a swamp in Louisiana. It's far from ideal, but it is far from Hanford, and that's one of the big reasons why the second detector was built there. And we'll talk more about that later. The detector design itself started off in the 70s, basically with the professor Ray Weiss, was a professor at MIT. He wrote a paper where he basically studied different sources of noise in an instrument of this kind, and he showed that this is possible. And then we had a period of 20 or 30 years of prototyping. The first detector, the one at Hanford, was inaugurated in 1999. And then Livingston followed soon after. By 2005, both detectors were operating. We had a few years of collecting data at the initial sensitivity. We saw absolutely nothing. Probably for about 10 years of analysis, of data analysis, we saw nothing. And then in 2015, the advanced version of LIGO was finished, which basically uses the same facilities, but bigger laser, better seismic isolation, and so on. And in 2015, the operation of advanced LIGO started. This is another schematic of the LIGO detector. You see over here is where the laser comes in, the laser beam. It comes through the beam splitter, which is sitting right here in this chamber. Then you see the two beams go along these two vacuum tubes. They're both 4 kilometers long, so about 2.5 miles long, high vacuum as well. And then you have two additional mirrors over at the ends, and the detector is located over here. Each of these chambers is basically a human size. You see a picture of it here. And they all have some version of an optical table, some sort of seismic isolation. And what you see here is an optical table that holds a structure. And this structure is what holds the mirrors in place. The seismic isolation is probably the most sophisticated part of the LIGO design. And that's basically because we're trying to measure vibrations at the level of 10 to the minus 19 meters. But the Earth itself is shaking, the ground right here is shaking at the level of 10 to the minus 6. So micron scale, right? So we need to suppress this vibration by 13 orders of magnitude, there or thereabout. And the way this is done is by a combination of active and passive isolation. So first of all, you see these pillars, like this one here. They're all hydraulically actuated on, and their purpose is basically to take out the tides, because tides are going to affect the mirrors, swing them left and right, and by millimeters. So these pillars basically have to move to counteract these kinds of strong forces. But then on top of these pillars, you see this platform here. This platform carries also a number of instruments like seismometers, geophones, and whatnot. They measure the motion of the platform in many different degrees of freedom. And then we act on it. We have feedback loops to try to cancel this kind of motion as well. This gives us about 5 or 6 orders of magnitude. So it's a very sophisticated setup, but it gives you only about suppression at the level of 1 part in a million or so. We need another 8 orders of magnitude or so to reach the 10 to the minus 19. So how do you do this? Turns out nature actually does this for us. If you're clever, you can get away with a lot without doing sophisticated sensing and so on. And the answer is just a simple pendulum. A pendulum itself is a natural filter for mechanical vibrations. So what do I mean? Imagine you have a pendulum, right? So you suspend it. There's a string. There's a pendulum bob at the bottom, right? If I move the top very slowly, right, the pendulum bob will follow, right? But if I move the pendulum the top of the pendulum, suspension point, if I shake it very fast, the pendulum bob will not be able to follow. You can give that a try, you know, at home. You can shake it very fast at the top, the pendulum bob will barely move. If you go through the math, it turns out that the suppression goes as 1 over frequency squared, right? So if your resonant frequency of the pendulum is about 1 hertz, and you shake at about 10 hertz at the top of the suspension point of the pendulum, the motion of the bob will be suppressed by a factor of 10 squared, so 100 times, right? And we just do this 4 times in a row, right? So you have 4 pendula on top of each other. Each of them gives you a factor of 100. In total, you get 10 to the power 8. And that brings you home, right? That brings you where you need to be. I mean, you know, the story is, of course, easy to say, but the design and the building of this took decades, basically. And it's probably the most sophisticated suspension system anywhere.
I have another question
Yeah.
online, and you might answer this later. John asked, could this be done in space, a la Webb telescope?
Yes, absolutely can. And there are plans to do that in space. Obviously, in space, you don't have to worry about vibrations on the Earth. And there are other things that you do have to worry about, but there is a project called LISA, which is based on, it's again an interferometer, but different type of interferometry than what I've described here, and much larger experiment. So think of a triangle with an arm of 2.5 million kilometers, and each vertex is a satellite, basically. They're sending light to each other, and you do interferometry with those. Because of this different, much larger arm length, the LISA detector will be focused on much longer wavelengths than LIGO. So things like millihertz frequencies for LISA versus 100 hertz or tens of hertz for LIGO. But absolutely can be done in space. All right. So this is the sensitivity I was describing. What's shown here, the schematic, is another schematic of the LIGO detector, and you see the more complicated topology than what I've described before. So again, here's a laser, here's the beam splitter, the 2 mirrors at the end, the detector, but there are 4 additional mirrors around here. This one here and this one here are called the input test masses, and they're designed to basically create a cavity in each arm, so that the light bounces back and forth between these 2 test masses in each arm of order 100 times, which allows us to increase the power in the arms themselves. And that allows us to get more sensitive to a small change in or small motion in any of these mirrors would create a larger signal. And then these additional 2 mirrors, this one here, the power recycling and the signal recycling, they're designed to take the light that's going back towards the laser or the light that goes towards the photodetector and send it back into the interferometer, recycle it again, and get additional improvements in sensitivity. So this, you see now that there is quite a few mirrors in there, right? If you count them all up, there is 7 primary ones, and there are additional ones that are not shown here. Each of those can move back and forth, but also pitch, yaw, roll, right? So you now start to see there are many degrees of freedom here, and you have to control each and every one of them in order for the detector to work. So there are hundreds of feedback loops in the LIGO detectors, and that is one of the most complicated aspects of it as well. And that's really needed in order to keep the interferometer in a locked position so that you can optimally observe. Let's see. So the curve that's shown here is showing strain. This is a fractional change in the arm length. So X arm length minus the Y arm length divided by 4 kilometers. And you see the sensitivity as it was about 7 years ago, 10 to minus 23 corresponds to roughly 10 to minus 19 or a little bit higher in meters. This is our collaboration. It's about 100 institutions, about 1,000 people, and here we are, University of Minnesota, scattered across the globe, literally almost every continent. This is our group here. We have 2 faculty, myself and Michael Kaufman. And at the moment, we have a couple of postdocs and something like 10 students, graduate students, and a number of undergrads. So when I was here 7 years ago, I think we were maybe 4 or 5 total. So things have grown substantially, of course, fueled by the discovery. All right, so this was our first detection, and this is, I think, in response to your question as well earlier. So 1.3 billion years ago in a galaxy far, far away, something like this took place. So what you see here is an actual calculation. This is not an animation. Somebody actually calculated 2 black holes rotating around each other with certain masses. What will happen to them? And the color scheme here shows the curvature of space caused by these 2 masses. And you see that as they get closer and closer, the curvature increases. It's maxed out when they merge. And you see that this object now is a new black hole, maybe. It rings a little bit and settles down, and you see the gravitational waves propagating outward. So there was a question earlier, what is the ringing about? Well, it comes from the fact that these 2 black holes, before they merge, the system is not spherically symmetric, right? If I rotate by a small angle, I don't get the same thing back. But the black hole at the end will be spherically symmetric. And it will be spinning because the initial system is spinning. So this process of merger and rotation and so on will produce gravitational waves until the remnant black hole is basically spherically symmetric. Okay, so I think we can just move to the next slide at this point, I think. All right, so this is my favorite animation. A billion years after that merger, September 14 of 2015, those waves finally reached Earth. And we all remember the terrible tsunamis of 2015, right? So that, of course, is exaggerated many, many times. But the key point is that the advanced LIGO detectors were on for the first time when this happened. And this is what our data looks like. So the top panel, the top 2 panels, I guess, are simply the recordings of the power fluctuation in the interferometers at Hanford and at Livingston. And you see the signal that starts off with a small amplitude and frequency, and over time it speeds up and it increases in amplitude as well, which is exactly this telltale sign of of a merging binary. The first thing you want to check is that the two detectors see the same thing, and you can take the Livingston's, or let's see, the Hanford signal and plot it on top of the Livingston one. That's shown on the right, top right, and you see that they line up pretty well. But they line up only if you shift one signal by 7 milliseconds relative to the other. And that is exactly because this particular signal came from the south. It hit Livingston first, and then 7 milliseconds later, it came to Hanford. The middle pair of plots is basically a prediction of general relativity. It's a numerical prediction. What the signal should look like if you have two black holes of certain sizes, certain masses, a certain distance away. And the idea here is to just show that these predictions of general relativity look very similar to the data itself. In fact, if you take the data, subtract the predicted models, you get this pair of plots at the bottom, right, or the third pair of plots. And you see just noise there, right? Which is to say that the general relativity predicts these signals very well. And this is actually a non-trivial statement. Up until this point, general relativity, of course, was tested in many ways, but they were all limited to relatively weak fields, right? You could test it in airplanes, you could test it in solar system, and so on. In this situation, we had two black holes. Each of them was about 30 times more massive than the sun, and they smashed into each other at the speed of about half the speed of light. It doesn't get worse than this, right? I mean, well, maybe, I mean, there are also, you know, black holes in the middle of the galaxy, which are millions of times heavier, but it's a crazy thing, right? And general relativity didn't have to work in a situation like this, but it passed this test with flying colors, and that's a really important message. Let's see. So I don't think we'll do this one. A few months later, we saw a second signal. This is what that one looked like. It didn't look. I mean, it doesn't look anywhere near as impressive, right? You can't see it by eye. You can only extract it by using what we call the matched filtering technique, where you basically multiply your data with different templates, and you find the best match. So that this technique allows you to dig out the signals from the noise, even if you can't see them by eye. These more sophisticated approaches allow you to extract things out of the noise. This one, for example, has 55 cycles in there, although you can't see them by eye. So it corresponds to somewhat smaller masses, for example, than the first one. On August 14, 2017, so a couple of years later, Virgo, this Italian French detector, came online. And a few days later, we observed the first binary black hole merger with 3 of these detectors. So now you can do complete triangulation, right? As we talked before, if you have only 2 detectors, you have 7 milliseconds time delay between them. There's effectively a circle of points on the sky where that signal could come from. But if you have 3 detectors now, then you can break this degeneracy and pinpoint better where on the sky the signal came from. Oh. And that turned out to be particularly interesting in the sense of binary neutron star detection, which I'll tell you about in a minute. So since 2015, we have detected about 100 of these events now. It has become old news, right? It's incredible, from first ever to 100. And now we can study their population. We can study how their masses are distributed, whether they're spinning or not. Are there equal mass contributors, or are there large mass ratios? Are there orbits circular, or are they eccentric? If they're eccentric, that would give you a signal or some hint of what the origin of these binaries is? I mean, are they formed by two stars that sit together, rotate around each other, go supernova, but they stick together and then eventually they merge? Or are they formed by more dynamic kind of situations, like in globular clusters? Maybe you have a high density of black holes. They interact with each other, and through this gravitational interaction, they hook in, two of them hook onto each other and become gravitationally bound, and so on. All of these questions are interesting for for understanding what is the astrophysics of the formation of structure, right? In these different environments.
Mark has a question online.
Yeah.
Do you want to just ask it, Mark? Are you still unmuted?
Had posted about several questions actually. The first one I did post there. What kind of signals are they predicting or expecting if you have like a multi-body, like several in once, or like a series, almost like the Shoemaker-Levy with Jupiter, that kind of thing. I'll get some other question I'll ask later.
Yeah, so I didn't quite understand. Do you mean something like having three black holes in an orbit around each other, or something else?
It could be three, or like a supermassive black hole for the center of a galaxy that sucks in several smaller ones at either at once or it's like a series of them.
Yeah, so in the case of multi-body systems, like having three similarly sized black holes and so on, I don't think we have explicit waveforms. The situation becomes very complicated, a lot of different parameters that you can tune. So it becomes difficult to make a prediction. And in general, they wouldn't all three merge at the same time, right? You'd probably have two of them merge, and then the third one maybe merges with the remnant. The other question you asked about the supermassive black holes in the center of the galaxy, there are more specific predictions, both in terms of small masses falling in. So this would be what we would refer to as extreme mass ratio situations, or mergers of two supermassive black holes themselves, right? That's also possible. And the signals for both of these are typically at lower frequencies, so below a hertz or even down to a millihertz or so. So it's more relevant for LISA, for example, the satellite-based experiment I mentioned, than for terrestrial detectors, which are limited to frequencies above, let's say, 10 hertz. Because for these very heavy objects, the merger would happen earlier at lower frequencies, basically. I hope that answers the question. I'm not 100% sure. Okay. All right, sounds good. Okay, so yeah, as I mentioned, so we now have these populations of binaries that we can study. We can study their properties and try to study what their origins are and so on. We're looking at their positions on the sky, their locations. So far, with 100, you can't really do that much compared to, for example, how the galaxies are distributed, where you have millions. But one thing that we have, for example, constrained is that we now know that every 15 minutes or so, a binary black hole merges somewhere in the universe. Okay, so these are not rare events, or maybe a different way to think of it is the universe is a very big place. And we observe individually detect those that are relatively nearby, but for each one of those that we individually detect, there are many more that are further away that are too faint for us to see with our current detectors. And also we know that we have observed multiple binary neutron star mergers as well, and we know that they happen roughly about once a minute somewhere in the universe again. Yeah. Yeah, waves are waves. They can interfere. Whether yeah, so if two such gravitational waves happen to arrive at our detector at the same time, we should be able to see them both. Yeah. They do. They follow the 1/r, so their amplitude goes as 1 over the distance.
Michael has a complex question. I basically think he's asking what happens if objects, instead of being in a relatively circular orbit, if they're coming in very eccentric orbits, or you know, almost like hyperbolic orbits or something like that.
Yeah.
What happens, and do they tend to circularize over time?
Yes.
Yes.
Yes, they do. If we are also interested in, and there are, so we get this data recorded, right? And then you have hundreds of different analyses that go through searching for different types of gravitational waves. And some of them are focused on exactly these highly eccentric orbits. The waveform that you observe, this rate of change of frequency and amplitude as a function of time, will be different for different masses, different orbits, different eccentricities, different strengths of the, well, we'll talk about that in a minute, so let me not go there. But basically, you can extract a lot of information about the system from how the waveform looks like, how it changes over time, how quickly it accelerates, and whether the acceleration in frequency is, the rate of change of frequencies is constant or is changing over time, and so on. So absolutely, you can see eccentric binaries. There are techniques to extract the eccentricity as well. For things like scattering, like hyperbolic orbits and so on, I mean, in principle, that's also possible, but the signal there is probably weaker.
Almost like DC sort of thing. You're looking more for AC.
Yes, yeah, exactly. Well, the scattering would be basically a blip, right? It would be a very short-lasting burst of gravitational radiation, and then nothing after that. So, in principle, it can happen. We may be able to see it, but it's harder.
I'm going to be selfish and ask my own question here real quick. My question is, could you ever get like two galaxies colliding in the central massive black holes colliding and creating anything that could actually create like the tidal type disruptions that would tear suns or planets apart? Is it that kind of a thing, or you could ever get anything, that kind of a gravitational wave that would tear things apart?
Yeah, so you're basically asking, can you have two supermassive black holes merge? And the question is, we think yes. We have not observed this yet. It would not be in the frequency band of LIGO, but it could be observed with millisecond pulsars. And I'll say a little bit more about that later, but there is a way of looking for gravitational waves at very low frequencies, at about 10 to the minus 9 hertz, 1 over a year. And this is where that kind of signals would be hiding.
And are those signals, you know, the distortions of space-time enough to start tearing things apart, or is it just?
But certainly near the black holes, near the central near the central black holes, definitely that should happen.
I wouldn't want to be that close anyway.
Yeah,
I need something.
yeah. There are observations of galaxies passing through each other. I think the bullet cluster is one of them, right? Yeah, certainly those things do happen. All right. When should I finish?
We have 15 minutes.
Okay. Okay. All right. Okay. No, I'm good. You know, I could talk forever. You know, it's just. Okay. Sounds good. All right. So I'll highlight one more thing then, which is this event of August 17, 2017. This is a different type of an event. So while, just to give you a sense, going back, this was the first one we saw. If you paid attention to this axes, this is this is 0.2 seconds long. So these 8 cycles took about 0.8 seconds. Sorry, 0.2 seconds. 8 cycles in 0.2 seconds or so. This one, if you look here, is about 30 seconds. And you see the trajectory very clearly in Livingston, this middle plot. You can see it clearly at Hanford. Can't really see it at Virgo, even though Virgo was certainly sensitive enough to see it. These, you're referring to, whoops, where's my mouse? Oh, there it is. These things? It's probably some noise. It might be a little too high for seismic, maybe something else. Too high in frequency, I mean. So two things to note. First, the length of this, how slowly it evolved, and the frequency evolution over time is an indication that this is a much lighter system. So this is an example of a binary neutron star, as opposed to binary black holes that we looked at before. And second, even though Virgo didn't see it, the reason Virgo didn't see it is because this event happened to be in the blind spot of Virgo. So remember, we talked during the outage, we talked a little bit about how the different polarization can couple or not couple to a given detector, or if a signal is coming in from a particularly well-chosen direction, it could stretch both arms simultaneously rather than stretching one and shrinking the other. So there are blind spots, both in terms of directions and polarization. And this one happened to be in the blind spot of Virgo, but that still means you could use Virgo for triangulation. We have online analyses that basically within a few seconds found out that this signal was coming from a particular direction of the sky, and we sent an alert to the astronomy community telling them, okay, something interesting happened there. And the scale of it was about 28 square degrees on the sky. So still pretty big for astronomy standards, but much smaller than anything else that we have done up to then, because typically our allowed regions were hundreds of square degrees. Now, in this particular case, there was a simultaneous detection of a short gamma ray burst observed by two satellite-based detectors, gamma ray detectors, Fermi and Integral. This has nothing to do with LIGO, nothing to do with gravitational waves whatsoever. Their signal came 2 seconds after the gravitational wave one. They also did a localization, and they found it to be in the same region in the sky. They also sent the alert. And then the rest of the astronomy community became very excited, because for the first time, we have a multi-messenger signature of an event in the universe. We have both light and gravitational waves coming from the same direction on the sky. So how cool can that be? Everybody turned their telescopes that way, right? Now, it took about 11 hours, I think, for Chile to become dark. And of course, that's where some of the best telescopes are. And they started to observe, and they saw it. They saw it in, I think, starting at visible and infrared, and then UV. And within days or maybe a couple of weeks, they observed it in every part of the electromagnetic spectrum. It was truly an exciting time. I mean, it was the science was happening faster than we could read email. There was so much excitement, so many people working on different things. It was really unprecedented. So this is the network of detectors, their locations. And if you look at all of these spots, you see that they're on every continent. There's even one at the South Pole. This is a neutrino detector ice cube, which looked for coincident neutrino signal at the time of this event. It didn't see it. Several spaceborne telescopes as well. The reason this was so interesting is because you could do science by combining gravitational waves and the electromagnetic signatures. You could do science that was otherwise not possible. And there are several of those things. I won't go into all of those details. It was a string of pearls, we called it. It was just really exciting. I'll mention just a couple. So first, neutron stars are forms of matter, right? These are basically giant nuclei. But we don't know what is the physics of such a dense form of matter. We can't reproduce it in a lab. But we have a way of probing it, right? There are theoretical models that say, okay, if you have certain mass object, it should have certain radius. So that this would be mass versus radius relationship. And some of these curves here show you, these are theoretical models that say how mass and radius of a neutron star should be related. But these models are speculative. There's a lot of uncertainty in them. And we now have a way of actually probing this. And this is how. If two neutron stars get close together, right, there will be strong gravity of one acting on the other. In other words, there will be strong tidal effects. And if the neutron stars are very stiff, they will not, they will remain spherical, right? They will not be stretched in any way. And the waveform will proceed in some particular way, right? You will get some gravitational waveform that will basically come from two spherically symmetric objects. Okay, that's good. But if the neutron stars are softer, then the gravity will start to elongate them. They will not be spherically symmetric anymore. They will become ellipsoids as they spin around each other. That will change the gravitational waveform. So by observing the gravitational waveform, you can tell whether the stars, these neutron stars, are being deformed by the strong gravity or not. And that tells you about which of these models of mass versus radius is correct. So this is the first time that something like this could take place. And there were multiple papers and some models are being ruled out and so on. But this is a really exciting aspect that we can probe nuclear physics using gravitational waves. This is another example. So this is actually one of the telescopes that observed this event in visible and UV wavelengths. I'll just make it play. You see in the upper right corner the time after the event, and you see that the spectrum was very blue at the beginning, focused on relatively low wavelength or high frequencies. And over time, it became more red. You can see that they became dominated by the longer wavelengths. And you also see these many peaks and valleys in the spectrum. Turns out these are signatures of what we call the R process, the process of forming the heaviest nuclei in the periodic table. So things that are heavier than lead, for example, and so on. And up until this event, we didn't really know where those elements are created, right? We know that the lightest ones are created after the Big Bang, things like helium, lithium, and so on. We know that stars, as they burn hydrogen, they create carbon, oxygen, and many other things. But we didn't know where the heavy things like platinum and gold are created. And this process and the peaks and valleys that you see here are signatures of different elements being formed as a function of time in this very dense and energetic environment where basically many nuclei are being smashed together, creating new nuclei and so on. One interesting tidbit here is that we expect about 1 Earth worth of gold was created in this event. Right. Order of magnitude, right? All right, so to finish off, as I mentioned, we have 2 additional detectors, working at the moment. So in total, there is 4 plus GEO 5. And LIGO India hopefully will be coming online in a few years as well. All of these detectors they're improving their sensitivity, then they observe for some period of time, then go down and improve the sensitivity again, and so on. So our plan, we're basically finishing up the latest upgrade. In April, we expect the new 4th observing run to start, go on for a year. We expect that these events, these binary black hole mergers and so on, will become daily. So there will be many, many more events coming our way. It's so many that we don't know how to analyze the data so quickly to keep up with the flow and so on. So different kinds of challenges. It's really incredible how quickly things have changed. We're also looking forward. The current facilities will probably be good for another 10 years or so. There are ideas of how to further improve the sensitivity and so on. But we're starting to think, what do we do after? And there are ideas. To deal with the seismic noise, perhaps Cosmic Explorer as well. These are probably 20 years away or so. The picture on the right is a picture of LISA, this triangular configuration with 2.5 million kilometer arms. Very different way of doing interferometry, sensitive to different types of sources, much heavier objects and so on. Pulsar timing I mentioned as well. The idea here is that you have millisecond pulsars are extremely good clocks. So you can basically measure the arrival time of each pulse, and you look at the fluctuations, right, of these arrival times. If there is a gravitational wave that passes between us and the pulsar, the length between the distance between us will stretch or shrink. The pulse arrival time will jitter. And by looking at many pulsars around with many instruments and so on around the globe, around the sphere, you can start to disentangle which of these which gravitational waves are going which way and so on. So this is a really exciting project as well. There is one in the US, Nanograv. There are a couple others across the world. They're also combining data in a kind of an international network. And they see excess in their data that they can't fully explain. So they have observed some, they don't want to call it signal because it's not strong enough. But it is something more than just simply the noise that they would expect in their data. So very exciting. The picture on the right here is the specific mode, the kind of B mode of polarization of the cosmic microwave background. So you may know cosmic microwave background was created about 400,000 years after the Big Bang. When the photons first decoupled from the primordial plasma. If gravitational waves were present at that time, they would have left an imprint in the CMB background, polarizing it in a very particular way. And that polarization is being searched for by the CMB experiments. There was one false alarm recently, but there are plans to make much more sensitive instruments going forward. So that will be very exciting as well. So to leave you with a message, every time we opened a new part of the electromagnetic spectrum, any new band of the electromagnetic spectrum, something new came out. We had discoveries, things that we didn't expect. With gravitational waves, we're opening not a new part of the spectrum. We have a whole new spectrum now to explore with terrestrial detectors like LIGO sitting over here in frequency above 10 hertz, with LISA and other satellite-based at around a millihertz, millisecond pulsars at about 10 to the minus 9 hertz, and the CMB B-mode polarization down at 10 to the minus 16 hertz or so. So a lot of interesting things could happen in that huge span of frequencies. We are expecting a lot of different sources to be peaking in these different parts of the gravitational wave spectrum. So stay tuned. We hope the future will be loud. Thank you. Oh, 9 o'clock.
Thank
Questions?
you very much. Sorry, is there a question?
This is Mark again. I'm a little curious about the setup, trying to find the locations and the difficulty of trying to actually tune these things to listen to what you want to hear and identifying the things you don't want to hear or detect. Geologic, man-made, heaven knows what other items you're trying to filter out. I'm kind of wondering what kind of difficulty it has been in determining all of that? Thank you.
Yeah, you know, whatever source of noise you could come up with, we're probably worried about it. No, this is where most of our efforts in data analysis go into. First of all, by having more than one detector, you can rule out most of these environmental effects, simply because even an earthquake that may hit, let's say, Livingston, will not show up at Hanford, or at least will be significantly reduced on that kind of length scales. There are things that exist that could be correlated on long scales, like, for example, magnetic field across the Earth is correlated because of the Schumann resonances. This can couple to different detectors at the same time and induce a correlation between them. We worry about this, and the way we battle it is we try to measure the magnetic field in different places with as good magnetometers as we can. In fact, we have hundreds of instruments that measure seismic motion, magnetic fields, microphones to measure the noise in the experimental hole, and so on, power line monitors, and so on. And all of those are recorded. So we have a huge amount of data that we use to basically vet each candidate signal to check whether something environmental may have contaminated that particular time, and so on. So that's, you know, very high on the priority list of the collaboration. We study these things in a lot of detail, all of these different environmental effects.
Yeah. Oh, geez, that's me.
I can repeat the questions.
So first, sorry, it's a two-parter. Is LIGO sensitive to both of the modes of polarization you originally brought up, the X and the plus?
Yes, but yeah, sorry. The question was getting late. The question was, is LIGO sensitive to both modes of the polarization? And the answer is partly. So if a particular wave, let's say coming straight vertically down onto the Hanford detector, is oriented so that it's 45-degree out of phase with the LIGO, with the detector arms, then that detector will see nothing. But that particular wave will not be so perfectly misaligned with the other detector. So the second detector at Livingston may actually see something. So the combination of the two can give you some signal. And depending on what direction of the wave is and its polarization, you can have worse or better situation.
In the same wave, have two components of polarization?
In general, yes. So just like light, you can have circular polarized situations as well, right? So you know, the story becomes more complicated. Depending on what source you're dealing with, you will have different type of, the polarization will behave differently, right? So in general, yes, you can have two waves with two different polarization, but it could be even more complicated than that.
And follow-up question, when you're trying to remove all the sources of noise, understanding that you came up with mechanical ways to subtract those noise components. Did you have to do it mechanically, or could you have done some of it mathematically? Like if you measure vibrations and you subtract it out of the data mathematically?
Yeah, so the question is to remove the
easier?
environmental effects like vibrations and so on, do you have to do it mechanically or can you do it mathematically? And the answer is we do both. If you can remove it mechanically, if you can do something to the detector to remove a source of noise, that's better. because then you don't have to spend hours figuring out the right algorithm to remove it in the data. But in practice, what happens is we do both. We remove what we can, and then other things sneak through, and after some time, we figure out that they're there. And then maybe use auxiliary channels like magnetometers and microphones and so on to filter the data and remove these effects. So in general, both of those approaches are taken. Yeah. Yeah.
Short question. Where would Lisa orbit?
Where would Lisa orbit? It's meant to orbit at the Lagrange point, so it will basically trail the Earth as it goes around the sun. Yeah, very soon. I think they're going to the same place.
The question is detection dependent on BDH orbits and now.
I'm not sure I understand. No, you don't. Of course, if the binary is aligned face on, that's probably the best scenario and the cleanest signal you can get. But if the line of sight is tilted relative to the binary orbit, then you will have some suppression, but you can still have some signal.
So unlike exoplanets, you don't have to just be lucky to be.
No.
I just have a question.
Yeah.
How often do they have to clean the mirrors?
You don't touch these mirrors. No, they come with a protective layer, which is removed when the mirror is already installed in place.
Mhm.
And soon after that, you close the chamber and you evacuate it, and you hope to never do it again. Because you know the specs for these mirrors are that their surface is I think 0.5 nanometer RMS. So RMS meaning basically average fluctuations in the surface are at 0.5 nanometer. Everything matters. A piece of dust that goes in and gets stuck on the mirror will effectively cause it will effectively heat up as the light passes through there, and this heat will deform the mirror enough that it will screw up the sensitivity.
And yet you built it in the desert and in a swamp.
Yes, well, they're both under vacuum. They don't know what's outside, but yes, that's right.
It's a good plan. I love
Yeah.
it. We're all good. Anybody else have any questions? Well, thank you very much, Dr.
Thank you.
Mandic. Appreciate it. All right. Well, I believe that concludes our meeting tonight.